All right, we're back. And we are going to go over a couple of things in this lecture, starting off with the estimated standard error of the mean, something that we discussed in the previous two lectures. The student's t-distribution, don't get thrown off by just the student because faculty also use it. One sample t-test, paired sample t-test, and the independent sample t-test. So today is all about the t-test. Huzzah! Okay, so just over what we've gone through, once we have produced some data, then we get into that exploratory data analysis. And within that, we go into inferences. But real quick, just wanted to point out back to this beautiful two paths that we've been looking at. This slide has been shown in almost every single one, and it's just to show, we get the tools for descriptive statistics, so that way we can have the tools ready for inferential statistics. And this is where we get into the t-tests. So this is one of those, as I've used in my analogies, this is one of those bosses that we're finally at. We're finally able to use all of the knowledge and power that we've learned and go forth amongst the t-test. So with hypothesis testing, a significance test starts with the development of a null and a alternative hypothesis. And this is something that we worked on prior to exam 1, and then we choose an alpha value for significance testing, and we establish that. So science sets a conservative standard to meet for a researcher to claim that they have made a discovery on a real phenomenon, which is where the significance comes into play. The standard is the alpha level, which is usually set at 0.05. The significance level, or the alpha, is the criterion used for rejecting that null hypothesis that we have set early in the step 1 phase. And for that, we can make better conclusions whether our findings rejects the null hypothesis or it retains the null hypothesis. And once an alpha has been set, the test statistic is computed. So each statistic is associated with a probability. Excuse me as I scroll down as I'm reading this. Each statistic has an associated probability that is called the p-value, which it kind of determines whether that, if it's going to be smaller than the alpha, then we would reject the null hypothesis. But if the p-value is greater than the alpha, then we retain the null hypothesis. So we compare those two, and from there, that is where we are calculating our test statistic, and that's where we kind of go back to. So we've practiced establishing null and alternative hypothesis. We're stating alpha levels and significance, and testing the statistic is something that we are going to do again, but it's no longer going to be with the z, it's going to be with the t. All right, so continue. So with that third step of testing a test statistic, there are some important questions before you move forward. So you always need to consider what your research question is. So are you looking at the differences in something, or are you showing an association of something? So for instance, with differences, you can look at differences in, say, gender. And that could be your independent variable, and your dependent variable could be amount of study time. So is there a difference between the two, or is there association amongst or a relationship amongst two variables? And with that research design, you need to think about those independent and dependent variables, and then also how you are actually measuring those variables. So is it nominal, ordinal, interval, all those. And then you always got to make sure with assumptions whether it is a parametric or a non-parametric. So a parametric test, what we've gone through before, is that normal distribution. So these make assumptions about the parameters that define the population distribution. And so if we base off our parametric test, it kind of goes well, within the parameters of a population. There's a lot of P's there. And these are more powerful than non-parametric tests because it basically follows more mathematical, let's just say, rules that are easier to better understand and follow within a certain guidelines. So non-parametric tests, those are going to usually be skewed, and they don't make assumptions about the distribution of the data. So these techniques are usually based on ranks or signs rather than the actual data, and are usually less powerful, but we will practice both. So just to provide some parts, I don't know why there's a question mark up there. It should just be a colon, but I guess, what are you going to do? So when you're comparing something, there can be a difference between a sample mean and a known hypothesis test. And so that's kind of what the practice that we have been doing is, we have been given scenarios in which we know the population and population mean of something, usually the standard deviation as well. And then we have like our sample mean, like our X bar. So that is a one sample t-test. And that's when it's parametric, right? So when we usually have been saying a normal distribution, again, that's with z-scores, but now we're doing it with t-tests, t-scores, we'll call it. And it can also be a non-parametric. You can also test something like this non-parametrically using the Wilcoxon signed rank test. So again, we'll practice all of these. Now, let's try a different comparison, and that would be, looking at the difference between the averages of matched pairs. So this is called a paired sample t-test, or a paired t-test, what you will also see. And so this is where you look at when you have like the pre and the post of something. And if it's parametric, then it is a paired sample t-test. If it's not parametric, you also use the paired Wilcoxon signed rank test. So the only difference here is that it is paired. So this is basically letting you know that it's the same people that you are testing versus the first one was just, you have one sample against the population. And then thirdly, we have the independent sample t-test, and this is where you are looking at two completely different groups. So the example that I gave earlier of gender and study time, the amount of study time, and that's a scale. And notice that we're looking at averages. So what is the amount, the average time? So if we're looking at those differences within means. So we're going to start off practicing with one sample t-test for comparing means. And the one sample t-test determines whether the sample mean is statistically different from a known or hypothesized population mean. We're going with that mu there. The one sample t-test is a parametric test, and it's also just known as a simple or a single sample t-test. And the variable that's used for the test is known as test variable. And we'll see this also in SPSS. In a one sample t-test, the test variable is compared against a test value, and that is like the population mean. And that is hypothesized on that mean, because again, we don't know what that is. It cannot compare sample means between two or more groups. That will be for other tests. So the requirements for this type of data is that the test variable must be continuous. So that is, it can have, it's a scale rank, right? So, or I shouldn't say rank, it's just a scale. There you go. So it's an interval or a ratio. So these things can go very high, they can go very low. But again, there has to be some sort of mean with it, not a proportion. And so the scores on these tests are independent observations. So there's no relationship between the scores and the test variable. So what that's saying is, if you were to do this test, your sample that you are comparing against the population, your sample really can't be related to the actual population. However, let's put a little asterisk there because we have to consider that a little later here. And the violation of assumptions will yield an inaccurate p. So if we don't make these assumptions, say if it's not parametric, and we do our p-value and we get a p-value, doesn't matter what, we are potentially getting a very wrong number, because if we don't make these assumptions, for instance, that the relationship between the scores and the test variable are not related or are related, then that can negatively impact our p-value. And when I mean negatively impact our p-value, I mean like the actual accuracy. It doesn't matter, again, high or low on that. The population sample from the data must be randomized as usual. That's a usual assumption within this. And normal distribution, it must be normally distributed of the sample and the population of the test variable. So non-normal population distributions, especially those that are thick-tailed or heavily skewed, considerably reduce the power of the test. So if you have wider and more frequent margins on the edges of your bell curve, then that's going to reduce the power, because honestly it's not able to be as accurate in its full assumptions. So among the moderate and large samples, a violation of normality may still yield accurate p-values. So we'll go over that, and again, that's kind of a case-specific thing, as well as what does the literature say. So I'll put an asterisk there too. So let's start off with an example. So do SIDS babies, and SIDS stands for Sudden Infant Death Syndrome, rather morbid, do SIDS babies have lower than average birth weights? Do SIDS babies have lower than average birth weights? So we know from prior research that the mean birth weight of non-SIDS babies in this particular population is 3,300 grams. And within our study, we studied 10 SIDS babies, and we found that their average was 2,890.5 with a standard deviation of 720. So we're looking at approximately a 400 gram difference in the average weight between the population and the sample that we have. So our research question is, does the data provide significant evidence that the SIDS babies have different birth weights than the rest of the population? I shouldn't have said full-on research question. This is just more our question here. All right, so what does our hypothesis look like? That would be let's start off with a null. Our null is the population of the population weight is going to be the same as the sample. That is going to be our null hypothesis. Whereas our alternative hypothesis is that our sample mean is going to be different than the population mean. And this can be looked at two tails, one tail, both left and right. So here we get to the lovely statistic. And what's nice about this is that this is just like the Z statistic that we've had. It's just that now we're looking at a different type of test with the T. So things may look the same. So we have our sample mean, we have our population mean, and then we have our standard error of the mean. So that is the standard deviation divided by the square root of n. Now, here's where it actually looks different as well, other than the T, is that this S, notice it is an S. Unlike prior, when we were doing with the Z, it was a sigma for standard deviation because this related to the population. I'm not going to write out population. That will take too long and I'll embarrass myself. So now we're looking at the sample standard deviation. And we always get our degrees of freedom by taking our n and minus by 1. So within our case, that would be a 9. So we would look this up in the back of the sorry, I shouldn't say the back of the book, fully back of the book, but what we have here is we are going to look at, there we go, just want to make sure, table C, or in the appendix, and that is page 545. So we'll get further into this. So, I didn't even know that one was there. Okay, well, here, I thought that looked a little funny right there. Okay, so this is where I want to start. All right, so our null hypothesis is, yes, that the average is 3,300 grams versus that the alternative is not 3,300 grams. All right, that looks much nicer. All right. So let's try out this data. I'm actually going to try this here with you, so that way you can see it here, and then we might be able to practice it. If this doesn't work out, then I'm going to delete this. Okay, so I have here, I need to open up SIDS. So if I'm going to go to book stats, I'm going to find SIDS here. SIDS, SPSS. Okay. All right, so here are our grams. And this is, remember, we know the population average, and so this is just our 10 that we actually received. So what we are going to do is we're going to go to Analyze. We're going to compare means because we have two means. And then we are going to go to one sample t-test because we only have one sample, right? And we have one population. So I'm going to take this sample and take it over here. Look at my options. I'm going to stick with that 95. We like that 95 in this class, and apparently in the whole academic. Okay, and this is where we put in our population mean. So that was 3,300. I'm going to hit OK. Okay, so this is what we have. We have our mean, and yeah, it's very close to what we mentioned, our standard deviation, and then our standard error of the mean. And here's our t-stat. Here's our df, that was n minus 1. And then this is our significance testing. And based on a 0.95, or should I just say like a 95% confidence, if an alpha of 0.05, this p-value is actually larger. So therefore, we would say that this is that there is not a statistically significant difference between that population average of normal babies and SIDS babies. So let's go back, and there is more data within the presentation, so let's just see what that looks like. This one, yep, okay, cool, yep, used it. Okay, so there's our stem and leaf. Everything looks rather normally distributed. All right, there we have that first, and then here's our next two. There we go. All right, so with that, let's just move forward to the next thing. And we wrote down our p-value. We have our t-stat right here, and based on a alpha at 0.05, we can conclude that SIDS babies do not have significantly different birth weights than the rest of the population of babies. Or you can also say SIDS babies do not have significantly lower than average birth weights. This kind of vernacular, this kind of talk, this is what I really want us to practice. And I need to practice it too at times. But it's definitely something that when it comes to our writing, when we turn in things, when we discuss, especially amongst the scholars, then we need to really take into consideration how we're bringing up these words. So again, SIDS babies do not have significantly different birth weights than the rest of the population. All right, so for effect size. Effect size is a measure of strength or magnitude of the effect of an independent variable on a dependent variable, which assesses whether a statistically significant result is, well, meaningful at all. So we will cover these on different inferential statistics, but just know that the effect size indicates the strength of the relationship or the magnitude between the independent and dependent variable. So within effect sizes, if we look at this here, we have table 5.5, and this is actually, I'm sorry, I don't have it within my notes of where this is directly from, but let's just look at it real quick. So effect sizes. So when we look at effect sizes, and we'll look at other examples, but this is just basically giving you an understanding of the different levels. So ideally, the relationship, if it's basically closer to 1, then it's a much stronger relationship. Where if it's down in the lower, say in the 0.2, then not so much. So let's just move forward with it. So going back to our SIDS example, going back to our SIDS example, if we were to look at the let me see this again. Okay, although SPSS does not calculate effect size for the single sample t-test, so what we just ran, I'm sorry, we can calculate Cohen's d, and that's a simple manner. So in short, a Cohen's d, and we're just basing it off right here, which is the difference over the standard deviation difference. Then we can conclude based on this number. So we were able to get, and let me draw this out. And this, again, we're just introducing effect sizes here, and we will go more into these. So, but this is within specifically just one sample t-test. So we have the mean difference, which is right here, found right here. And then we have the standard deviation, and that's right here. And then we were able to get a negative 0.57, and again, that's still in this range. We just go within a 0 and 1 number, and so we have a medium to large relationship strength. Okay, so it's all right. We can trust this data is kind of what it's saying. It's like, okay, there's some strong relationships between that. So moving forward, a one sample t-test that compared a mean weight of SIDS babies to the weight of the population was conducted. No significant differences were found, and then you put the t-score as well as the p-value. The sample mean of 2,890.49 grams was not significantly greater than the population mean. This is a really good example, I'm just going to circle right there, of how you would see something like this in a manuscript. So when it comes to our presentations, take note of something like this example of the full-on calculations that it provided. All right. So we have different sample sizes to look at our effect sizes. We can go more into this later, just kind of wanted to still provide this information, as I think all information from previous instructors are very helpful. Okay, if you wanted to run a non-parametric test, here are the instructions, but we're going to move forward because we're looking at paired sample t-test. So, paired sample t-test is a parametric test, so normally distributed, and this test is also known as a dependent t-test, a paired t-test, a repeated measures t-test. So there's so many things that you can be called. There's so many t-tests already, and so let's keep it simple. We have 3 t-tests, parametric t-test, and we went over one, and now we're under the second one, which is paired sample t-test. So these compare the two means from the same individuals, the same object, related units, just something of the same at 2 different times. Consider it maybe the treatments or the conditions over time. So these are also, as I mentioned earlier, these can be considered like pre and post, and you can even do a pre-post and then a post-post. Those are actually very common, and the purpose of these are to decide whether there is statistical evidence that the mean difference between the two pairs made a significantly different outcome from the first to the second. So the data must meet certain assumptions. And first off, the dependent variable must be continuous. Again, these have to be scale form. They can't be like percentages. You can't plug in a percentage for any of these t-tests. And for the pair t-test, the paired measurements must be recorded in two separate variables. So what that's saying is that they can't be under like the same column. They have to be in two separate columns in order for this to actually be ran. And they must be related samples or groups, or that's also considered dependent observations, meaning they have to be the same. So if I tested the class on something, then I better collect, specifically student A. Their data must line up with student A when I do, like, say, a post test, and so they just have to match. It must be random, and it must be from data from the population in which you have done your literature review, you've done your information on, and it must be normally distributed, which is why it's parametric on this one. And the outliers, no outliers in the difference between the two related groups. So in other words, everything should be kind of nice and steady. What I've seen a lot is you remove the outliers if they are, you find the standard deviation of, say, the pre-test, and then anyone who scored outside of, say, 2.5 standard deviations, then you just remove them from the entire test, because they do skew the data when there are outliers, because again, we're dealing with means, which is much more sensitive to those types of changes. So when testing these assumptions of normalities and outliers, you must use the variable that represents the difference between the pair values. So although I mentioned like the pre-test, what we're talking about is actually the differences. So we are using you're pairing your each test, and you're subtracting to find that difference, which is going to be the D. So in other words, if I tested the class and student A scored 75 the first time and then 85 the next time, I would find the difference between that, which is 10, and I would do that for all individuals and see if there's any outliers from that specifically. So when one or more of these assumptions for the pair test are not met, then you run a non-parametric Wilcox-Ensign rank test, and that is found also in SPSS under non-parametric. So the normality condition for these applies when it's the distribution of the mean and not the population. So again, we're moving away a little bit from the idea of using population in mu, and we're really just looking at the sampling distribution. So we're looking at those X bars. Sounds like a candy. X bar. Therefore, it's okay to use procedures for the paired t-test when the population is normal, and the population is normal, and there's at least, when the n is between 5 and 10, but honestly, the bigger numbers are going to have better, even if it's going to be a little skewed. Having a higher n is going to be nice. So can a T procedure be used? So data set A is skewed, as you can see here. I don't necessarily know. I mean, it has more than 5, so that's all right. But then I don't really think it should, and neither does this PowerPoint say that you should use a t-test for this. Because notice that you have a lot of numbers in the 20s, a lot of values in the 20s, and then you have this random one way out here in the 50s. Okay, so let's look at data. Let's look at B. And we have, okay, an n of 25. That's nice. Okay, and if you notice that there is kind of a little bit of a curve here, we would go with, yeah, let's use a t statistic. And then let's look at data set C. So again, this one is definitely skewed one way, but then there's also this way outlier out here. So let's call that a no-no. All right, now let's start practicing these. A hypothesis can be expressed in two different ways. So you can say that express the same idea mathematically equivalent. So we can just say within our hypothesis test that our null hypothesis is that both populations are the same. That's this top one right here. Whereas our alternative hypothesis is that the first mean is going to be different than the second mean. It's not going to equal the same. We can also say that the null hypothesis is the first mean minus the second mean and would equal 0. So we're just saying that there is no difference. This is the exact same as this again. Whereas the alternative hypothesis is saying that the first mean is going to be different, that the first mean minus the second mean is not going to equal 0. Haha! So there is a difference. Okay? So let's go a little bit further into this. So a study addresses whether oat bran reduces LDL cholesterol with a crossover design. Subjects crossover from cornflake diet to an oat bran diet. Wow, what living! So half the subjects start on cornflake and half start on oat bran. 2 weeks onto the diet, then they measure the cholesterol, and then there's a washout period where you allow time to recuperate, and then you switch the diet. So then there's 2 weeks on diet 2, and then you measure the LDL levels. Okay, so our hypothesis test is saying that the null hypothesis is that there is no difference. So this average difference is equal to 0 versus the alternative hypothesis is that there is a difference that is not equal to 0. So we do our t-stat, we find the difference between the two means, and we subtract it from whatever the no difference is. And then we find our standard error of the mean. And so this is going to be our standard error of the difference and divided by the square root of our n. And then we convert to a p-value, table C, or we can use a software. And then we determine whether that p-value is smaller than our alpha. And then we find the conclusion for it. So let's go ahead and give this a shot. So we have oat bran. Let's open up oat bran. All right, I'm just gonna exit out of that one. We're good. Appreciate your help. I'm gonna go to oat bran. You know what's nice is I have no idea how many of you watched this, so I'm just enjoying just talking like it's normally myself because I'm getting used to this. Okay. So we have our cornflake diet. This is, again, their LDL cholesterol levels. We have our oat bran diet. And then we have our differences here. So just wanting to point out that we are subtracting from the first one minus the second one. So this is going to be our mu1. This is going to be our mu2. Not the Pokemon. And so we have 4.61 minus 3.84, and we get a 0.77. So note that we're not doing mu2 minus mu1, we're doing mu1 minus mu2. Just pointing that out. All right, so let's go ahead and follow the rules. Now I already know what we're doing, but I want to make sure that we have this. So we are going to create a stem plot. We are going to create a box plot. We are going to run descriptives on all variables, including the delta variable, and then we're going to run a paired t-test. So the paired t-test is the last thing that we're doing here. Okay, so let's start off with the stem plot, shall we? Okay, so if we go to Analyze, and we go to Descriptives, we go to Explore. Explore is the fun stuff. So we are just going to, I'm just going to dump all of these into the dependent list. I hope this works. pretty sure this is what I'm trying to, yep, okay. We just wanted to confirm. All right, and so with our stats, I'm just going to leave the descriptives at 95, and then with our plots, there's my stem and leaf. Did it want anything else? Okay, we want a box plot. Okay, I'm pretty sure this already gives me a box plot, and then we want descriptives on all variables, including the delta. So we have that. Check, 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 and I'm going to hit continue on that, and let's see what we get. All right, so we have our cornflake diet. We have our oat bran diet, and then we have our difference. Okay, so our mean here, 4.64, and then our difference, or our oat bran is 4.26, and then so if you were to subtract those, we would get 0.38 as our difference mean, and so there's all of our lovely information right there for us, so we don't have to calculate anything by hand. All right, so this is our cornflake diet. Okay, there's our stem plot. Okay, it looks rather cornflakey, average. Okay, here's our oat bran diet. Already off the bat, I'm noticing some difference here. Okay, so already I'm noticing that there's a lot of threes in there, whereas up here the threes are up at the very top. There's 4 within the threes. Okay, all right, and then let's look at our differences. Now our difference actually gets much smaller, and there is our box plot. Now the challenge that I'd like to do in class is use them, put all of these into one graph so you can actually look at the difference. That's going to be fun. We're going to have a great time. The difference. The difference. The difference. Okay. Enough being weird. Nah. All right. Then we're running a paired t-test. Okay, here we are. So what I'm going to do is I'm going to minimize this, and to find the t-test, we are going to go to Analyze. We are comparing our means, and then we are paired sample t-test. And you can see their little logo here is A1 minus A2. So that's what we're doing here, mu1 minus mu2. So let's make sure that our variable 1 is going to be cornflake. Yep, sure is. And then our variable 2 is going to be oat bran. Let's see what our options are. 95, yes, okay. And let's hit OK. And what do we get? Okay, so here's our paired sample t-test. It provides the means for both. Again, we saw some of this up at the top here. And then we are looking at the correlation here, but what I'm really wanting to look at right here, right off the bat, is whether they're significant or not, significantly different or not. So I come down here to the paired sample t-test, and I scroll over here. Let me expand this a little bit. There you go. The significance is 0.01. So if our p-value was at 0.05, if our alpha was at 0.05, then our p-value is smaller. Therefore, we would reject the null hypothesis, and we would say that there is a statistically significant difference in their diets. So let's see what our presentation shows as well. Okay, here we go. So there's our stem plot. We saw that earlier. Beautiful. There's our box plot, and this shows a slight negative skew. Okay, yep. This is something that I wouldn't really ask, but if you were fully describing something, say in a research project, then you might want to show that. And then we have our descriptives here. This is what we just went over. Okay, then we compared the means. Okay. So this first table, so we went over this part, so it shows just the means being compared, and the standard error of the mean right here, this is the statistical term that measures the accuracy which the sample represents a population. So in statistics, a sample mean deviates from the actual mean of a population. That deviation is the standard error of the mean. So this is how much these are basically being different from the mean in terms of numbers. values, I guess I should say. So the second table, I skipped over this because I wanted to go straight to that pair t-test. I knew we were getting here. So this tells us about the correlation between the variables and that it's a significant correlation. Okay, and we can tell that by looking at our significance here. It is small. In fact, so small, everything's just zeros. These variables are highly correlated. And this where it says correlation, again, the highest that it goes to is 1. And this is at a 0.87 or 0.88. So we want them to be correlated at a high level, but not 1, because that would mean that we are measuring the same thing. That's too much. So, you know, as 0.99 is nice, and so is this number right here. All right, then lastly, we look at our paired sample t-test, and real quick, let's just start from the left here. So the standard error, so we know the mean, we know the standard deviation, but what is the standard error of the mean? So this, again, this is looking at this sample that we have and how much the mean of this sample deviates from the actual population, which we don't know, and that is that. That is the standard error of the mean. Okay, then we have our upper and lower level confidence. We learned about this in chapter 10. And then we have our degrees of freedom, and this represents the number of individual values that a statistical analysis can estimate. So you can also think of this number as the number of values that are free as you estimate the parameters. I always like to say it as like, this is how many differences you can look at it. And then lastly, I want to make sure I'm hitting everything. Yeah, there we go. And then we have our significance right here, and we'll look over this beautiful thing on the next slide. Okay, so we have our hypothesis. So was there a difference? Our null was that there was no difference. Our alternative saying that there was a difference. We did our t-stat. We found our t-stat. We did our degrees of freedom. We found our degrees of freedom. We calculated our p-value via computer, and we found evidence against the null hypothesis, because the evidence against the null hypothesis was at an alpha of 0.05, and therefore our alpha was smaller than that. However, if our alpha was at 0.01, we just missed the mark on that because we are at 0.011. Oh, so close, but that's still statistically significant. So we can conclude that LDL levels on the oat bran diet were significantly lower than on the cornflake diet. So again, if you were to sum this up, if you were to write this in a project, a manuscript or a presentation, a paired sample t-test was calculated to compare the mean LDL cholesterol levels for a cornflake diet to the mean LDL cholesterol levels of an oat bran diet. The mean LDL on the cornflake diet was 4.64 mmol. This dash L. I'm going to skip all that. The LDL levels between the cornflake and the oat bran diet were significantly different, and then you would put in the t stat as well as the p value. All right, going back to that Cohen's d, looking at the effect size, if we were to go back to our little calculation here, which is looking at the difference of the mean, which right here is going to be right here at the very beginning, and divided by the difference in the standard deviation. So this right here. And what we calculate is negative 0.88. So that is pretty darn strong. So what this is telling us is that we have a pretty strong relationship between the difference that we found within our study. There it is, our sample size. Okay, so we can do this with a non-parametric test, but I'm going to move forward because my mouth is getting dry. And we can do a non-parametric using a paired Wilcoxon test, We can go over that in class as well. So let's go to the independent sample t-test. So these are also known as, these are a lot of also known as, we have independent t-test, independent measures t-test, independent two samples t-test, student t-test, two sample t-test, uncorrelated scores t-test, unpaired t-test, unrelated t-test. Do you want to hit me in the face? Probably t-test. The variables that are most commonly used, the variables used in this test are known as dependent variables or test variables, as well as independent variables or grouping variables. So I know that there was a lot of words that I just said, but what we need to know is that independent t-tests compare the means of two independent groups in order to determine whether there is statistical evidence that the associated population means are significantly different. Again, this is a parametric t-test. So again, just like all of the other t-tests that we've discussed, the dependent t-test, the dependent variable must be continuous. It must be on a scale that can go from 0 to 100 to 1,000, depending on whatever you're looking at. Think height. Think weight. Think of... There's plenty of more out there, and I totally froze when I started to try to think about it, so I'm just going to move forward. All right, but then the independent variable needs to be categorical, so also known as nominal. And these need to be in at least two or more groups, so you can't have just one group. That's not an independent t-test. You need two or more. And so therefore these should have some sort of values to them as well. So with an independent t-test in the samples and groups, there should be no relation between the two groups. So unlike the pair t-test where we looked at, student A at the beginning of something and the student A at the beginning or at the end of something, this is looking at student A from class A, and then we're looking at student A from class B. Two completely different students, even though I just mentioned student A, but they're in completely different classes. Two completely individuals or units, observations, however you want to look at it. Again, the example I gave earlier was gender for this one. Okay, so there should be no relation. That means that they're independent. Subjects in the first group cannot be in the second. So none of them within the entire study can be in one group and the other. And there can be no influences. That really comes into play when it comes to testing, in control groups. Did one participant, if there was say a professional development in one class but not a professional development in another, but then one of the students happened to drop in on the other one, that's basically influencing your tests, your subjects, or participants is a better word. So these are the assumptions that must be made. If they are not made, then your p-value will not be accurate and you run the risk of a type 1 error, maybe even a type 2. Okay, so again, it must be randomized. It must be normally distributed. And this is where we get the homogeneity of variances. And so this is basically making sure that the variances across both groups are equal. So when this assumption is violated and the sample sizes for each group differ, the p-value is not trustworthy. But you should know that the independent sample t-test also includes an approximate t-test that is not based on assuming equal population variances. So what this is saying, and I'm just going to sum it up right now, is that it's better off to have two independent groups of similar in. It's better to have, in other words, it's better to have two groups of 500 than one group of 500 and another group of 250. So that is an assumption that must be met. However, when we calculate these, what we're saying is that there will be a calculation already to say hey, you know what? I already considered that one has half of the amount of the other, but I'm still going to see if there's any sort of significance. That will be tested here. So so when they cannot be assumed, we can use the Welch t-test in order to look at the separate variances. And I'm reading that, and I just want to go back, and I mentioned the example of 200 people, and that's the sample size, but we also must consider the variance. Okay, so think about the tails, how wide the tails are. So if there is a greater variance, that's a much wider bell curve, you need to also make that into your assumptions for independent t-tests. So that's where variances, also standard deviations, come into play. Okay, thank you for listening. For the data requirements, there shouldn't be any outliers. And when one or more of these assumptions are not met, you are going to want to run a Mann-Whitney U test instead. So a couple of the things to kind of consider is that each group should have at least 6 observations or subjects, participants, or more. So more than 6 would be ideal. Inferences for the population will be more tenuous with too few subjects. Again, the more the merrier in this. And then a roughly balanced design where there's the same number of subjects in each group are ideal. And if they are highly unbalanced, so like that example of an N of 500 versus an N of 250, then you are possibly violating some of the requirements and assumptions for just the validity of the independent t-test. All right, so let's look at an example. Do fasting cholesterol levels differ in type A and type B personality men? And we're looking at the data of milligrams per deciliter in a Western collaborative group study. Okay, let's look at it that way. The null hypothesis and the alternative hypothesis need to be looked at. So you can say it again in multiple ways. You can just say that mean 1 is different, let's try that again. The null hypothesis is that mean 1 is the same as mean 2. The alternative hypothesis is that mean 1 is different than mean 2. Again, we have another example down here. Okay, so we state our hypothesis, whether it's two-tailed, one-tailed, either left or right. Just do all of them for fun. And we determine our t-stat. So we take the average of the first mean minus the average of the, I shouldn't say the average of the first mean. We take sample mean 1 minus sample mean 2, and we divide it by the standard error, which we determined by finding the standard error of each difference of the sample mean 1 minus sample mean 2, and we square root that. Fortunately, with all of this, it's fun, but we have calculators and we have computers. So we're going to convert that t-stat to find the p-value within our software and significance level. So we're looking up WCGS. Sounds like a radio station. Okay, so I'm going to exit out of this old one. I'm going to exit out of this old one. I'm going to exit out of that one. Yeah, I want to proceed. Yeah, I want to proceed. Okay, WSGS. Stands for what could go south. Okay, here we are. So we have, right off the bat, I just want to see what we have here. We have a total of 40 individuals, 40 observations. And they are divided into groups. So this is really beneficial when you have the groups already labeled out here. This is going to be our categorical, our independent variable, and I can just tell that by, if I was to get a data set, that's the first thing I kind of notice on, this is a group between group 1 and group 2, right? Whereas this is our dependent, because if we're running an independent t-test, then this must be a scale or continuous. Okay. So we are going to go to Analyze. We are going to go to Compare Means. And here is our independent sample t-test. So within the group, let's put in our group into our grouping variable, our independent variable. Whereas our dependent variable, we are going to put in our test variables here. So we have a 95 confidence interval. And here you have to define your groups. So I see group 1 and group 2. So when I go here, I'm actually going to stay with that, with group 1 and group 2, because you might have, like, in your data set, it might say, let's just say it's male and female. It might say M and F. This is for you to also just signify what are we putting in here. All right, so let's see what we got here. We found all of our lovely data, and there's a couple of things that we can look at. Here's what I want to do. I want to go through the PowerPoint presentation, and then I want to go through this again, because I felt like that might be a little bit smoother. Okay, so we're going to do the following. We're going to do a side-by-side stem plot. We're going to do a side-by-side box plot, and we're going to run descriptives. We're going to do that in class, actually. I'm not going to do it right now. Okay, but here they are, side-by-side box plots. Okay, here is our graphs. So we get to look at the cholesterol of group 1 versus group 2. And we were able to look at this by splitting file, move to group. You can do those into your own histogram. I just want to get straight to the fun data. Okay. Oh, excuse me. I should say this, though. We should always explore and explain what the data shows. I'm just going faster because I've been lecturing for a while. So, it mentioned the location for this. It's actually saying, like, group 1 is larger than group 2, and the spread, I don't really like this way. This isn't a way I would necessarily show it. I'm going to go through that in class. Okay, so our descriptives here, we have our minimum and maximum mean, standard deviation, and then we also have it by group with our percentages. This is a good way just to confirm your number here, because if you are familiar with your own data and you're like, wait a second, that should be 21, then you need to go back to your data, and that stuff is never fun when you have missing values. Okay, so this went a little bit further with the descriptives and I just went straight to independent t-tests. So this is where I wanted to get to. So we have our grouped statistics here. We have our independent samples here. And if we look at this bottom part, this is if the variance is significantly different. All right, so we are looking at the differences within our variances. So if we were to even go to our standard deviation, we can even tell right here that our standard deviation is pretty different. Is this statistically significant? Okay, getting to the fun part. What we have here is what we pulled up in our SPSS. And we'll start off with looking at Levine's test for equality of variances. And what I first look at here is the significance. And okay, if we were to go with the idea of the 0.05, that's usually where our threshold is on an alpha, then we say it's significantly different, right? Well, this is 0.263. So if we were to even do a hypothesis test and use this significance, then we would say that's not significant, right? That being said, that's not what we're doing with this number, but that concept of significant versus not is still there. So this shows whether or not there's a difference in the variances of the averages. So by looking at this, it is actually showing that there's not much of a difference between the two variances. Now, although if we look back here, our standard deviation, and we're off by like 8, that's not so much telling us as much as we can just look at this. So because this is not significant, because it is not below 0.05, then I would move on with assuming that the variances are equal because they are not different. Now, moving forward, then I'm going to look at this. So I'm just going to use these. So if the variances is significantly different, so if this was 0, so let's just say like this actual number was like 0.02, then we would use this one, but we're not, because it's 0.263. So we're going to look at this independent samples t-test, and we're going to look at this significance. Therefore, and I know that there's really not much of a difference here, but when you look at this and you need to ask yourself, well, which one do I use? You're going to focus on Levine's test to determine that. And so I determined that our p-value is at 0.014, and therefore with an alpha of 0.05, then I would reject the null hypothesis. So here it is written out. Consider this when you start doing your tests. All right, we calculate the effect size, and what we have here is a little different equation, but we find our D right here. So there actually is not much of a relationship between the two. So again, this is just adding up another part of statistics, which is the effect size. And that is something that is not calculated in SPSS, but we are able to calculate it by hand by looking at the mean 1 minus mean 2 divided by the pooled, which is this beautiful equation. Other software does this. I'm moving forward. So if it was non-parametric, we would use a Mann-Whitney test. And again, the groups must be independent of each other, must be in 2 different categories, and the dependent variable must be continuous. And so we will do that in class because I feel like that's a nice place to stop.